All right, we're going to start talking now about covalent compounds and drawing out their basic Lewis structures. All right, but a quick review on those chemical bonds. When we talk about why do atoms bond, well, remember, the atoms are going to bond because we're going to have that positive and negative attraction between atoms. The positive center of the nucleus of one atom is going to attract the electrons of the other atom, and vice versa. Okay, and as those atoms get closer and closer together, this attraction is going to help stabilize them. Okay, that's why these atoms are going to bond, is the stabilization of energy. How are these atoms going to bond? Well, these atoms are going to be formed by that transfer or sharing of electrons between atoms. Okay, but keep in mind, valence electrons are going to be the only electrons involved in this bonding process. All right, then we had the three types of chemical bondings. We had ionic bonds, where we had the transfer of electrons. We had covalent bonds, which was the sharing of electrons. Then we had the metallic bonds, which was this electron sea or pooling of electrons. Also, don't forget that if I have a metal combined with a nonmetal, that's going to be electron transfer. That's going to deal with ionic bonding. If I have a nonmetal combined with a nonmetal, that's going to be electron sharing, and it's going to deal with covalent bonding. Then if I have a metal with a metal, that's going to be electron pooling. That's going to involve metallic bonding. Right now we're going to deal with just that nonmetal combining with a nonmetal to have that covalent bonding, or the electron sharing. Okay, now don't forget about Lewis symbols. Lewis symbols are a way for us to represent these atoms in their valence electrons. Based upon their groups, that determines how many valence electrons we have. Okay, so don't forget, we're only going to deal with the valence electrons here. All right, so let's talk about a covalent bond itself. It's going to be this sharing of electrons. So if I look at hydrogen, Lewis symbol for hydrogen would be an H with one dot. So I've got two hydrogens. If they come together, we form a bond between them. That bond is formed by sharing of their individual electrons. It's not transfer like ionic bonding. One hydrogen doesn't pull the other electron away from the other. They end up sharing their electrons between each other equally. Okay, so what happens is that positive center of the hydrogen is going to start to attract the electron of the other hydrogen, and vice versa. And as they get closer and closer together, that attractive force is going to hold those two atoms together. It's going to help stabilize those atoms. Now, when dealing with covalent compounds, nonmetal combined with a nonmetal, we have to worry about something called the octet rule. Okay, in this sharing of electrons, we're going to share electrons in such a way that we're going to end up with 8 electrons. All right, so if I look at my chlorine, chlorine has 7 valence electrons. So I've got 2 chlorines. As they come together, their unpaired electrons there, they're going to share them between the 2 chlorines. Why? Well, without the electrons being shared, each chlorine would only have 7 electrons. When they share that electron within that bond, each chlorine technically now has 8 electrons. Right, so that bond between them has 2 electrons that's shared between them. So each chlorine in this picture has 8 electrons. What does it mean with that 8 electrons? Well, that's the octet rule, and more importantly, it's that idea of the noble gas core configuration where we're getting that S2P6 combination. So these atoms are going to be stable when they're surrounded by 8 electrons, or 4 electron pairs, if you will. So each of those chlorines has 8 electrons around it. Now, another way we might represent that, instead of showing the 2 dots of the shared electrons in between, we use a single line between them to represent a bond. Okay, that's a covalent bond because those electrons are shared. Keep in mind, though, that single line represents one bond, and it still has those 2 electrons in it. We've just drawn a line in its place instead of showing those 2 electrons. Okay, it just makes it look cleaner. Keep in mind, with all these bonds, whenever you see that line between 2 atoms, it represents 2 electrons being shared. All right, so we're always going for this S2P6 noble gas configuration, or the octet rule. We're trying to get 8 electrons around each atom. There's different ways we can do that. If we look at CH4, CH4 has 4 bonds around the carbon. Each one of those lines, remember, represents 2 electrons. So around the carbon, we have 8 electrons. Now, one thing to note, with hydrogens are only going to ever have 2 electrons. They'll never reach that octet rule. because at most, hydrogen can only have 2 electrons. It's in that n equals 1 subshell, which means if n equals 1, all I can have is L equal to 0, which means all I can have is an 1s orbital, and that can only hold 2 electrons at most. So hydrogen is always happy with just 2 electrons. But focusing on that central atom there, the carbon, it's got 8 electrons around it. Another way to get that 8 electrons, if we look at NH3, that has 3 bonds around the nitrogen and a lone pair. Remember, each one of those lines represents 2 electrons, so as far as the nitrogen is concerned, it's got 3 bonds, so that's 6 electrons, plus 1 lone pair at the top. That's 8 electrons total. Let's look at water. Around that oxygen, we have 2 bonds and 2 lone pairs. We've still got 8 electrons, it's just a different way of getting that 8. So always take into account each single line represents 2 electrons. And then we have to worry about those lone pairs. All right, another thing we can look at to get this octet around these atoms is we could form multiple covalent bonds. Let's look at CO2. If I look at a Lewis structure for CO2, it's, okay, I've got that carbon double bonded to one oxygen, double bonded to the other oxygen. So with that carbon, remember, each line represents 2 electrons. So within that double bond on one side, I've got 4 electrons, and the double bond on the other side, I've got 4 electrons. I've got 8 electrons total. Let's look at the oxygens now. Oxygens each have a double bond to them, so that's 4 electrons, and then they have 2 lone pairs, so that's another 4 electrons. They have the octet. Okay, we could look at C2H4, which looks like this. Carbon has a double bond to another carbon. That's 4 electrons shared between them. And then each carbon has got a bond to 2 hydrogens. So that's another 4 electrons shared. So each carbon has 8 electrons around it. If we look at N2, N2 has a triple bond between the nitrogen atoms. Each one of those lines represents 2 electrons. They're shared between both nitrogens, so they count for both nitrogens. So we've got 6 electrons in the triple bond, and then each nitrogen has its own lone pair. So that's 8 total. Okay, so there's different ways we can get to this octet rule when we draw out Lewis structures. But when we go to draw these Lewis structures, remember, we're always trying to shoot for that octet rule, and we do that either with lone pairs or bonds. All right. Let's look at drawing Lewis structures now. We're going to have some steps listed out here. I'm going to read through them real quickly, then we're going to go through examples following those steps. Follow these steps. They're going to get you the right Lewis structure. Okay, but follow them exactly as we go along. Okay, don't skip a step. Don't try to do any shortcuts. Follow these. You're going to get the right Lewis structure. Okay, so the first thing you're going to do is you're going to count all the valence electrons available for all the atoms in our compound. Then you're going to draw the skeletal structure. So I'm going to show you what that is in an example here. That's usually going to involve the lower electronegativity atom being in the center, but that's not always the case. If you're dealing with oxygen, a lot of times that's going to be an external atom. Or if you have hydrogens, those are going to be external atoms. Okay, but in general, that lower electronegativity is a good way to predict what the central atom is going to be. Then we're going to count 2 electrons in each bond from that skeletal structure, and we're going to subtract that from our total number of valence electrons. Next, we're going to complete the octets and the atoms attached to the central atom by adding lone pairs, and we're going to subtract those electrons from the total. Any remaining electrons we have left, we're going to place on the central atom in pairs and subtract those from the total. If at that point the central atom doesn't have the octet, we can then form double or triple bonds so that the central atom can get to the octet. All right, and then lastly, we're going to calculate formal charges and minimize those if possible. These are the steps. Keep these in mind. We're going to show the steps and go through them right now, but whenever you go to draw Lewis structures, it's good to have these steps in front of you and to use them. All right, so let's use them to look at NH3. Step 1 was count all the valence electrons available. Well, nitrogen has 5 valence electrons. Hydrogen has 1 valence electron, but there's 3 of them, so we get a total of 3 electrons from those 3 hydrogens, which gives us a total of 8 electrons. So I'm going to write total of 8 electrons, and I recommend you just write it off to the side and keep track of how many electrons you have left. That way you can see how many electrons you have left and what they're being used for, because if you forget to subtract electrons or you don't subtract them properly, it's going to throw your answer off. It's going to throw your Lewis structure completely off, because all of these bonds in the Lewis structure and all of these lone pairs in the Lewis structure are going to be dependent upon those valence electrons. All right, so next I'm going to draw the skeletal structure. Now with the skeletal structure, I said it's going to usually be the lower electronegativity atom in the center. What is electronegativity? Let's talk about that real quickly. Electronegativity is going to be the preference of one atom in a chemical bond for electrons. In other words, if I have two atoms bonded together, even though they're sharing electrons, they're not sharing necessarily equally. Something has a higher electronegativity, it pulls those electrons in the bonds slightly closer towards it. It doesn't completely remove it, but there is that unequal sharing when we're dealing with these covalent compounds. The main thing with the electronegativities, if we look at a periodic table, as we go across a row from left to right, electronegativities are going to increase. As we go up a group, electronegativities are going to increase. If you can remember that fluorine's the largest and the francium's the smallest, well, how do I go from the smallest in the lower left-hand corner to the largest in the upper right-hand corner? Well, in order to go from smallest to largest, I have to increase as I go up a group and increase as I go over from left to right across the row. So in looking at this, if we look at nitrogen, it's got electronegativity of 3. Hydrogen's got electronegativity of 2.1. We said that the lower electronegativity is going to be the central atom. We also know in this case it's going to be a little bit easier than that. We don't have to deal with the electronegativities because hydrogen is never going to be a central atom. Okay, it's just not going to happen. So when I draw out the skeletal structure, all I'm going to do is put that nitrogen in the center and then have a single bond connecting all of my external atoms. So nitrogen with a single bond to each individual hydrogen. Okay, that's what I mean by that skeletal structure. Not putting any other lone pairs in there. All I'm doing is drawing the central atom, external atoms, drawing those single bonds in. All right. Next, for every bond I have formed in my skeletal structure, I'm going to count it as 2 electrons, and I'm going to subtract that from the total. So, how many bonds do I have? Well, I have 3 bonds in my skeletal structure. That's 2 electrons in each bond, so I have a total of 6 bonding electrons. So I started with 8, I lose the 6, I'm left with 2. Okay. Next step. I'm going to complete the octets of the atoms attached to the central atom by adding pairs of electrons, and then I'm going to subtract that from the total. Well, since my external atoms are hydrogen, hydrogen's always happy with 2 electrons. So at most it's ever going to form is 1 bond. It's never going to have any lone pairs. Okay, so the hydrogens are happy here. So I don't add any extra electrons to my external atoms. So the electrons to those attached atoms, 0. So minus 0, I still have 2 electrons left. What's my next step? I need to place any remaining electrons in pairs on the central atom and then subtract that from the total. Well, how many electrons do I have left? I have 2 left. How many pairs is that going to be? Well, that's going to be 1 pair. Those have to go on the central atom. Regardless of whether the central atom has the octet or not, when you get to this step, any electrons that are left over have to go on that central atom as lone pairs. Have to. Okay. So I've got 2 left, which means I add 1 lone pair to the nitrogen. Subtract those 2 electrons, I have no electrons left. Step 6. Central atom does not have an octet, form double or triple bonds. Well, nitrogen has 8 electrons around it. It's happy. So I don't need to worry about this step. Okay? Last step, calculate formal charges and minimize if possible. Well, how do we calculate formal charge? Well, formal charge is going to be equal to the number of valence electrons of a specific atom minus the number of bonds attached to that atom minus the number of lone pair electrons. So let's look at nitrogen. Nitrogen has 5 valence electrons it starts with. How many bonds does it have around in this picture? It has 3, so 5 minus 3 minus the number of lone pair electrons. Well, there's 2 lone pair electrons, so 5 minus 3 minus 2 equals 0. So nitrogen in this structure here has a formal charge of 0. Let's look at the hydrogens. Hydrogen starts with 1 valence electron, minus the 1 bond each hydrogen has to it, minus 0 lone pair electrons, so each hydrogen is equal to 0. Okay, so formal charges on everything are 0. There's no way to minimize it, because 0 is the smallest we can get to in terms of minimizing these formal charges. So we don't have to do anything else with those formal charges. Mainly with these formal charges, what they're doing is they're looking at how many valence electrons did an atom start with, and technically how many valence electrons is it ending up with when it comes to this sharing within these bonds. Okay, so you can see here I've drawn lines through those bonds. If I represent each bond by 2 electrons, those circles there, if I separate out an electron to either atom in that bond, you can see for the hydrogen on the left, it ends up with 1 electron. Right? Well, it has 1 valence electron and ends up with 1 electron. It's true of all those hydrogens. The nitrogen, if it gets 1 electron from each bond, that's 3 electrons, plus it's 2 in the lone pair, that's 5 electrons. Well, nitrogen started with 5, it's still ending up with 5. That's really what the formal charge is looking at. Nitrogen started with 5 valence electrons, it technically ended up with 5 electrons. Okay, that's not always going to be the case with some of these. All right, but that's just a picture showing that. All right, so when I look at NH3, my Lewis structure would be this, using those rules. Okay, but follow those steps.